Thank you for the invitation. Thank you for coming with so many choices going on. Um, right, so I'm going to talk about complexity of algebraic objects. Period index problem, I think it's roughly what I'm going to talk about. I think that was actually the title. So this is, not a super serious talk. I'm going to try to give like a survey of, some ideas, some history, some conjectures. Towards the end of the talk, I'm going to pretend to prove something, and to try to yeah, but probably everybody will be tired and asleep by then. But we'll see how it goes. But just relax and here we go. So the three parts to the talk. First, this is so surprise for those who didn't know, this is a talk on Galois cohomology, and I will try to explain why everybody cares about Galois cohomology, whether or not you think we did. And then I'm going to talk about the period index problem for the Brouwer group in the second part, and then period index problem for higher cohomology. Right, so first, introductory stuff. So just to kind of like ground our notions for a moment, what is field arithmetic? Means different things to everybody, I'm sure. But so given a field F, it's natural to ask, how do you determine whether or not a system of polynomial equations has a solution? This is typically what maybe people think of as field arithmetic. Or perhaps, how do you describe the structure of algebraic objects over some given field, like this, your favorite algebraic objects, maybe are division algebras, those are mine, but maybe quadratic forms or various other kinds of things. And these questions turn out to be closely kind of interrelated, and a big tool in dealing with both questions is Galois cohomology. So a natural question that you might be asking here at the Summer Research Institute in Algebraic Geometry is, why am I in a talk on field theory? So you are. This is where you ended up. It's possible, I mean, that maybe you're interested in, solving equations over fields other than C. I mean, this is the third week after all, so this is like legitimate. But I also want to mention that, like, I mean, for me, one interesting thing about working just looking at fields and field arithmetic is that many interesting kind of geometric questions that you might look at are not obviously, but kind of surprisingly birational questions that are really questions about function fruits. And so I'm just for kind of entertainment's sake, if you haven't seen it, and I don't know, just at a scan, I can see that a third of the people have obviously seen this example before, but it's still kind of fun. Just like, why does this kind of thing come up? So for example, somebody gives you like, let's just say X is a curve, a smooth projective curve over a field K. We all know there's this thing called the Picard variety of the curve. And what kind of nice property is the house, somebody gives you a line bundle, you associate that line bundle with some point in the Picard variety. But unless you're over an algebraically closed field, this question turns out not to be so obvious. Like, if you have a point on the Picard variety, does it actually, is there a line bundle actually associated to it? If you're over an algebraically closed field, the answer is yes. If your curve has a point, even the answer is yes. But in general, for some given point, there is an obstruction for lifting that to a line bundle. The obstruction turns out to be an element in the Brouwer group of the field. So I'll tell you about Brouwer groups in just a minute. These will come up, right? So just for the moment, the Brouwer group is the second cohomology group, which you think of as either Galois cohomology, which is a kind of continuous group cohomology, or you can think of it as the étale cohomology group for spectrum of the field. And interestingly, so this is really a question about like one specific point and one specific, does it come from a line bundle? but you can kind of like ask this kind of more globally, like kind of not just for a single like rational point, but you can ask for kind of like in families, like for the whole, oh, what did I say? Burr. Oh, okay, mistake in my slide, sorry. So that shouldn't be Burr X, that should be Burr of pick there. So like instead of just a single point on pick, you could ask like kind of globally, and in this way come up with a cohomology class, not on Burr X, but on Burr pick X, which is the second cohomology group of pick X. So sorry about that typo. And what you can find out is that this, to check if these obstructions vanish, if it vanishes at every particular closed point, it actually suffices to check that this obstruction vanishes at the generic point of, well, not X, but pick X. So in other words, you know, it just like hurts me every time I say I wrote X instead of pick X. All those X's are pick X's. I'm sorry. I'm sorry. Sorry. Okay. So anyways, this reduces to a question about Galois cohomology over a field, even though a priori it's something maybe about étale cohomology of pick X. And so generally, you know, this isn't just about pick. This is a kind of like a general thing that happens with a lot of interesting kind of moduli spaces. You know, and so these Brouwer classes naturally come up as like obstructions to like fineness. You can think of obstructions to the existence of some universal object, that kind of thing. And the higher cohomology groups arise in analogous ways, not exactly in this way, but you can think of them as like obstructions that kind of come up with regard to other kinds of torsors in maybe perhaps more subtle ways. So, you know, like, I don't know, if you're looking at like G2 torsors over something or other, then H3 might come up and that kind of thing. Okay. So Galois cohomology. Again, you know, this is kind of not, this is probably familiar, but so the main character is going to be this group Hn of C mod LZ. So this, and by the way, if you care, when I say this, I'm not really necessarily exactly thinking this. I'm kind of imagining that maybe Z mod L is replaced by roots of unity with some twist that we haven't really decided, or maybe like by some kind of like mixed or bad characteristic version of it. But I'm just kind of pretending this whole talk that I have whatever roots of unity and I'm not really kind of like thinking too hard. And that, you know, I'm kind of ignoring all of these kinds of issues, unless I'm not, but please don't worry about it too much. Okay. So anyways, the kind of the working definition for us then is this is really like some sort of continuous group cohomology in the absolute Galois group with coefficients in Z mod LZ. Why does one think about these? As I kind of mentioned before, these are kind of natural repositories of interesting kinds of invariants and obstructions. The structure of these groups just holds a lot of information about the field arithmetic. And I'll just kind of mention, there's no reason that I actually should mention this. I actually had another slide that I erased that I don't actually need this anymore. But I'm just saying, like, you can do some like bad characteristic stuff as well. It's not just about kind of roots of unity and things like that. Okay. So now we're kind of halfway through the introduction. I think I'm actually on time so far, which is kind of I haven't given like a real slide talk since like the pandemic, I think. So and there's no like page numbers. So I think so if I like start like talking really slowly at some point, it's, you know, because I totally misjudged. So but so far we're doing okay, I think. Okay. So, you know, we're halfway through the introduction. I'm going to now kind of just give you some basic facts about Galois cohomology if you haven't seen it before, that'll kind of like say all of the kind of basic things that we'll need. It won't take very long. Okay. useful properties. So if somebody gives you some group, algebraic group or whatever, H1 with coefficients in that group classifies algebraic objects with automorphisms G. I can make a more precise statement, but I won't. And as an example, quote unquote, if you have just like the cyclic group, Z mod LZ, this classifies cyclic Galois extensions of our field. Which, because I'm assuming kind of roots of unity are around, are given by Milnor theory is just, things modulo. Okay, that's H1. What about H2? You can get the flavor of H2 by kind of bootstrapping off of H1, which is the way I'll explain it. So if you think about what H1 with coefficients in GL does, well, this kind of classifies things whose automorphisms are GL. That would be classifying really vector spaces is what that translates to. And not surprisingly, there is only one vector space. And so this H1 is actually just trivial. It has just a single, it's like 0 or whatever. If you do H1 PGL, it's a little more interesting. PGL is the automorphisms of the matrix algebra. And so H1 PGL ends up classifying what are called central simple algebras. You can take it as a definition that these things are things which at the algebraic closure look like matrices. And more specifically, Wedderburn-Artin gives just a kind of more implicit structure of these things. They're matrix algebras with entries in some division algebra. It's not an arbitrary division algebra. It's an F central division algebra bidimensional over F. The center is F. And if you think about this kind of natural short exact sequence where you identify PGL with GL mod scalars, and you look at the kind of long exact sequence, what you see is you go, so I'm pointing on this board because I don't have I was going to say I don't have two arms. I don't have two pointers, so it's over here. So, you get H1 of this, which is trivial, H1 of that, which is, central simple algebras, goes to H2 of this. And so this gives you a way of saying if associated to a central simple algebra, I get an H2 class. And it turns out that that H2 class really kind of obstructs the triviality of that H1 class. It tells you whether or not it came from, well, the point basically, which is to say whether or not it's a trivial central simple algebra. It's just the matrix algebra. All these kinds of invariants that you get, you can kind of stick them together and get this thing called the Brouwer group, which by definition is just this H2 for now. But what does this Brouwer group end up telling you? It's the obstructions for these things being matrix algebra, but you can kind of squint your eyes and think from Wedderburn-Artin that obstruction is the D. And it turns out that this H2 classifies the Ds. So the elements in the H2 are literally isomorphism classes of division algebras, and that's one way to think of them. And so, so that's H2 with coefficients in GM, and then it turns out that, because roots of unity we're kind of squinting and ignoring, this H2 Z mod L is exactly the L torsion elements of the Brouwer group. Okay, so now I've told you what H1 and H2 are, and of course, then we can go to H3. Okay, no, I won't do that. Instead, I'm going to now quote this kind of amazing result, what we used to call the Bloch-Kato conjecture, and what we now call the norm residue isomorphism theorem, which says, it gives a presentation for all of these cohomology groups. So altogether, they're a ring, a nice graded ring, and the result of this norm residue isomorphism theorem is that as a ring, it's generated by H1, and the relations, which are explicitly given, are in H2, and that gives you everything else. Everything is kind of generated by H1 relations in H2. And of course, now we understand that H1 is basically cyclic extensions, H2 are basically division algebras, and altogether this tells you kind of everything in some sense. These explicit generators as a ring, the kind of multiplication is called the cup product. So these are kind of how we write the kind of natural generators in this way. Okay, is that all good? I mean, well, so this is like, yeah.
So there's no relation, like if you have two things, you look at the quaternion algebra with squares equal to those two things, yeah, it's trivial, it's not beautiful.
Yeah, so in other words, exactly, the relations are given, you could just say it as when is the, so if you're looking at L equals 2, it's literally when is this quaternion algebra trivial, and that is when that's all that's going on. More generally, the explicit relation is that kind of famously is, so it's given by just two guys. If you have just like an A1 and an A2, the relation is A1 plus A2 is 1, which is just absurd. If the things add up to 1, that the cup product is trivial, and that generates the relations. It's like, it's as if somebody thought of it as like a joke, and then it was proved to be correct. You know, I mean, I don't know. So it seems to me. Okay. So, okay, so, oh, I guess this is where the lack of page numbers gets me. I thought I was like, there's more introduction, and I'm not sure how much more. So, okay, behavior of cohomology classes. Okay, so we know that we're generated by these kind of like lists of cup products, which we call symbols. And based on this, we have this kind of measurement of, which you think of as a measurement of a complexity of a cohomology class, which is how many symbols do you need to explicitly write it, right? So you define the length of a cohomology class to be the smallest number of symbols that you need to express it as a sum. In practice, if you kind of know how alpha came about, if it came from some concrete way of making it, then, well, in principle, if you know how it's made, you kind of know that there's some way to write it in an explicit way. In practice, it's very, very difficult to make this thing work. But morally speaking, like some generic construction gives some generic list of things, and those lengths should specialize to any particular member. But this is like super subtle in practice, and the bounds that you get are really hard to actually get concretely in practice. Yeah.
Wait, is it obvious that it's not bounded on the whole or separate end?
So depending on the field, it may not be bounded on the whole of H upper N, and I'll get to that in the next slide. Exactly. Yeah. So the slide that I erased was describing in like some very kind of basic cases, like even though you think like here's like a super concrete expression for a class, like how many symbols do you need? They kind of like for very easy things to write down, they like balloon massively. So you can write down, for example, this is the thing that I erased, and I shouldn't talk about it because I removed it. But still, what I'm just going to say is like, you can take something in mod like L squared cohomology and write it as a cup product there and say, what if it magically came from L cohomology? Like if it had period L instead and it lifted back there, then how many things would you need to write it? So this was this was kind of like done in the case of H2 in bad characteristic only by Merkuriev and a collaborator back in the early 80s. Then it was done in characteristic 0 last year for H2. Then, by the way, how many do you need? You need like, I mean, like a lot. I mean, kind of exponentially many kind of things, depending on like, you know, I'm not exactly, I erased the slide, I don't know. But, you know, and then like, you know, me and some collaborators did it in bad characteristic for higher cohomology last year. But it's like, it balloons, it's giant. You start with like one symbol and then you need like, you know, L to the L symbols or something, you know, it's like, it's really bad. Yeah, so life is harder than it should be with symbol length. Even obvious things kind of blow up in your face. Okay, now, so this is just for a particular class, but what if you said, like, what if you looked at a given field, like Jordan was just asking, and you said, if I look at all possible classes, I might ask, like, what's the biggest number of things I need? Now, if somebody gives you a random field, like really like some interesting field, I'm supposed to be done with my introduction. Okay, if somebody gives you a really random field, you might need a whole, like, you might need arbitrarily many. So you might be able to find a sequence of cohomology classes where each one needs more than the last one, and there might not be an upper bound. So very natural, simple fields. But not so natural. It's not the kind you're going to bump into, it's the kind that you're going to have to make, you know? But anyway, so there's this kind of the uniform length bound of a field is the biggest you have to get. This is, you can think of as a bound for how hard it is to construct elements in cohomology. But there's an analogous thing called the index, which is a bound for the destructibility of elements. How hard or easy is it to destroy elements in cohomology? So the definition of the index goes like follows. So you look at all possible finite degree extensions, and you look at the ones such that your cohomology class maps to 0 when you extend the fields. And you look at the GCD of all the degrees of field extensions where you split it. In most cases that we understand, the GCD is actually a minimum, but I've actually no idea if it always is. And then just like we have this like uniform length bound, there's like the uniform splitting dimension bound, which is kind of like how big can this index be? So these are kind of two parallel measures of complexity. So just some easy observations are that the length bound dominates the splitting dimension bound. And the reason is that if somebody gives you a bunch of cup products, if somebody gives you a cup product is multiplicative. So if any of the things in that list dies, the whole cup product dies. And for any one of them, it's given by knowing whether or not something is an elf power. So you can kill it by extracting an elf power. And if you do that for each one of each symbol in your list, then that means that you can construct a splitting field, which is the number of things in your list. So that's one bound. Also, if your field is algebraically closed, none of this stuff matters. Everything is 0, and so, you know. The other thing is that if you're looking at H1, well, everything is just a single thing, a single symbol. That's all that is in H1 by definition. And so the length, everything, you either have 1 or 0, 0 if you're algebraically closed, basically, if you are close to that. Those are some easy observations, and those are basically the only easy observations I know how to make offhand.
Power of L.
Yeah, that's my question too.
Oh crap! Okay. Okay. Here's what I should have said. It's the okay.
You can just say yes.
Just write on this.
Okay, this put like a log-based L in front of index. It's how big a power of L you need is what I actually mean for splitting dimension. So I meant kind of like the exponent of L that you need. Crap. Yes. So there's like, so there should be, so it's not really the index that's like the power of L, which the index is, or something like that. That is really what I'm imagining. Crap. That's the splitting dimension. Okay. Okay. Sorry. Thank you. Okay. Oh, okay. I'm only 4 minutes behind. Okay. So that's okay. So these are what we know about in general about index and splitting dimension and lengths. Now what I'm going to do is I'm going to specialize to the case of H2, where there's kind of a lot of kind of like more interesting interpretations, a lot of famous results. So let me now talk about the kind of period index problem, which is to say, what can you say about the index? Really, that's what we're talking, or what can you say about the splitting dimension, as I put it. So let's start with what we might call the classical period, starting in 1905 with Wedderburn's little theorem. Wedderburn's little theorem says there are no finite division algebras. And what that says is that if you're over a finite field, there's no H2. And so that means that the 2 length and the 2 splitting dimension are both 0. There's nothing going on. The next big statement is around 1930, the Albert-Brouwer-Hasse-Noether theorem. And what that says is that if you have a global field, what they showed is that everything is actually a cup product. Well, if you have enough roots of unity, then it's just a cup product of 2 things. So in other words, both the length and the splitting dimension are 1. It's like a single symbol when symbols are, okay. For the next result, we need to have this notion of the Sin-Lang property on Diophantine dimension. So you say that a field has this kind of Sin-Lang property Cn if whenever you have a homogeneous polynomial of degree d in enough variables, d to the n variables or more than d to the n variables, then there's a non-trivial 0. The Diophantine dimension is the smallest n that you're Cn for. And so conjecture, and I guess I should have said that Sin's theorem is then that SD2L and length 2L are 0 if you're C1. I should have said that. Okay, that's also part of the classical period. Theorem of Artin from 1982 says that if you're C2 field, then the 2 splitting dimension is 1. So in other words, everything is like a single symbol when you have roots of unity and all that. But only for L, a power of 2 or 3, some 2 to some power, 3 to some power. Okay. So now you might kind of, I never like these kinds of notations because it's like you just have a bunch of like indices floating around and you're supposed to get some intuition about like what's going on. And I think this notation kind of like obscures the intuition. But my goal actually is the notation is supposed to be depressing. Okay. So like, because like the thing is like, what we would like to know about is like, how is it like to split a cohomology class? How hard is it to write them down? What do we know about this? And the point is like, if you like put a few indices here, we only know about like a couple values of some of the indices, for very special Fs. Okay, so that maybe, so sorry, I guess I'm just being a downer. Okay, coming into what we might call the modern period, here's what we have started to learn. So I guess the modern period is like when I'm in grad school or something like that. No, it's okay, but that's still classical. Yeah, thank you. Yeah, thank you. Okay, so if you the first of these kind of newer results. Starting in 97, if you have a finite extension of a p-adic function of p-adic functions in one variable, so these are p-adic function fields, then this thing is 2. Concretely, what that says, there's another way to kind of like phrase these things, which is on the one hand, you have the order of the class in the cohomology group, the so-called period, and you have the index. And the question is like, what divisibility properties do you have? So this thing, the period divides the index and the index divides some power of the period. And how much bigger can the index be than the period? And what this says concretely is that the index divides the period squared. So the period can be square bigger than it, but it's not kind of arbitrarily bigger. So Saltman did the case where P does not divide L, and then later on it was, as part of what they did, they added the case where P divides L in the later paper. Johann was able to prove this conjecture of Artin in the case of a complex function field. So if you have a complex function field, then he was able to show that, again, in this case, this says that the period and the index coincide. So I was, the slide was not carefully written. I was going to say, and then Max did the kind of like the bad characteristic case, but then I realized I had written C. So there's no bad characteristic case, but Max did the case where C is replaced by some algebraically closed field as characteristics. Okay. It divides L. So guiding the progress towards these things was this, what became this kind of folklore conjecture, which was kind of phrased by Krashen and kind of really kind of like written down and espoused by Max Lieblich, which is that this two-splitting dimension. So again, this is about saying how big Brouwer classes can be, how complicated they can be. And the statement is that the splitting dimension is bounded by the Diophantine dimension -1. So, which it's kind of like why should it be the Diophantine dimension -1? Like what's the intuition there? I'll try to say a little bit about that a bit later. And so towards the end of the of this modern period, we have again some kind of further you can kind of think of it as like an extension of the results of Saltman. Instead of like over a function field over a p-adic field, it's something like a function field over a like very iterated field where little k maybe is QP, or maybe it's finite field or things like that. Kind of a variation of that original theme, just kind of like a higher local field kind of thing. And in that case, the conjecture turns out to be true. So this is a result of Max's and a result of mine with David Harbader and Julia Hartman using very different methods. So that brings us to the postmodern period. And so now what is the postmodern period, technically speaking? So starting at 2014, I'm not sure, it's kind of, controversial exactly what distinguishes the postmodern period from the modern period, I think. But I think it starts with this theorem of Max Lieblich, which says, with Parmal and Suresh, which says that this two-splitting dimension is bounded by 5 if you assume a heavy-duty conjecture of Koyo-Talan about Brouwer-Menine obstruction being the only obstruction to rational points on certain kinds of varieties. I feel like I apologize for this talk at this point. I think like these slides are really a little bit boring right now, right? We're going through this long list, okay? What do I want to say? Okay. These results are more exciting than I'm making them out to be. Okay. Yeah.
First of all, I like your slide. The second of all, my question is, I just kept noticing there's like a lot more about SD than there is about length. And I'm wondering, is that because SD is like more important, has more applications, or is length much harder?
Well, yeah. So I think nobody had any idea how to say anything about length up until this middle of the postmodern period that you can kind of see if you squint a little bit. It was so the length bounds are really kind of interesting. So they're like, it's kind of like one could give another totally separate talk, but like the flavor of like what people know about length bounds originally was all about like lower bounds. Like how you need it. I know I can't do it with 1. How many do I need? Can I do it with 2? Can I show that I can't do it with 2? Do I need 3? That kind of thing. Like what's the lower bound that I know I must have to have to write a general class? And so you get these lower bounds that are, that are like, that look like, for example, like there was this thing about like central symbol algebras of index 8 and period 2. How many things do you need? You need in general at least a length 4 thing, and this was like a big deal or whatever. But then like you might start asking like, what's the maximum that you need? What's these upper bounds? And we never actually knew anything about getting good upper bounds until this result of Monseries. But the upper bounds are crazy when you actually like kind of like pull them out. Like, so you can use Monseries bound for this like degree 8 thing, and you can say, okay, well, I know I need at least 4. What's the maximum that I know will make it work? And so, you know, and well, maybe, and sorry, not with the 2 and 8, but with like, say, I don't know, 3 and 27 or something like that. The upper bounds end up being like in the gajillions. They're just like ridiculous that you get out. I don't know if it's actually a gajillion, but it's pretty big, yeah. But so like, generally speaking, originally people didn't know much about upper bounds for length. And there was just this, right, so first Max showed this thing for surfaces over finite fields that you can get away with 2. Monsery finally came up with a length bound, which says that if you have a finite Diophantine dimension, you get length bounds. But the length bounds depend on L, so to speak. So here, L is p to the t. And the lengths are big. You know, so if the length behaved like the index is expected to behave, it would look more like Diophantine dimension. It would just look like Diophantine dimension -1. But instead, there's the t times p to the t. You know, it's a different order of magnitude. And then, okay, so for function fields over p-adic surfaces, you know, this result with Osher, Venantio, Colin Ingalls, and Max, where we get 4 or 5. But what I wanted to highlight is that, except for Max's results, all of these bounds are too big. Like, none of these things are the correct conjectural bounds. You know, we don't have, and yeah, so if you want to say, like, what do we know, for example, about algebraic threefolds and these bounds, we know like nothing. Okay, finally, we're in the contemporary period, and let's see, so I guess okay, yeah, okay. So in the contemporary period, I think this starts actually with this paper, which is therefore ahead of its time, because, you know, it gets counted in the period above it, discriminant avoidance, which says that in the case of H2, you can essentially reduce to looking at kind of actual geometric cohomology. You know, you can, so if somebody gives you a cohomology class, what did I say? Somebody gives you a cohomology class over the function field of some algebraic variety, then you can find some other cohomology class over some other algebraic variety, which is not over its function field, but geometric, such that the kind of period index problems for these two things coincide. So you kind of lose control over what class and what variety you're looking at, but it's still about like a cohomology class and a variety of the same dimension that's kind of geometric. And because of that, it makes it more interesting now to think about how do we understand kind of period index for things that are coming from unramified classes, from classes that are geometric. And for those, there have been some really beautiful recent results. So we get the kind of correct result for abelian threefolds using kind of a very different set of more Hodge theoretic techniques. We have bounds for particular varieties. If somebody gives you a particular variety that's geometric, this recent result of Hoybrucks and Matai tell us that you can get an index bound on a particular variety. So this is kind of like it's not a bound for the function field, it's a bound for things in the function field that come from geometric classes. Okay, that completes the what we know about the H2. All this stuff was about H2 and nothing about higher N. higher cohomology. So let me just say a bit about the higher cohomology. So the evidence seems to show, kind of from circumstantial examples, that Galois cohomology groups tend to start small, grow in complexity, and then come back down. And just as like a silly example, I thought I would give this one, which I hope is roughly correct because I came up with it on the plane. I think it's probably fine. But like, okay, so if you look at like this field and you look at the Galois cohomology, it actually looks like the exterior algebra. And so you can like ask about kind of symbol length problems for exterior algebras. And there are these kind of funny conjectures about kind of like how many like, you know, wedges you need to write down a general wedge and stuff like that. And you get the following length bound for this field, that it's roughly this horrible thing, the ceiling of D choose in, you know, divide by whatever. But, you know, you kind of squint and asymptotically, this is roughly 1 over n squared, d minus 1 choose n minus 1. And which means that, you know, that as, you know, as you let n vary, n is the kind of cohomological degree, it kind of like grows and then shrinks. So these fields are really not typical. They're very, and this particular behavior is very special and is not to be expected, but the broad flavor of this behavior is, I think, you know, reasonably typical, the kind of growing and then shrinking. Okay. So to kind of put a general conjecture out there, by the way, really what my goal in this talk is just to like state some random conjectures that I think would be, that I want people to work on, you know, to put me out of my misery and all that. But so like for a dimension D field, what seems to be true? Well, always the first one is 1. The second one is conjecturally D minus 1. That's this period index thing. And the last one, circumstantially in some examples, looks like it's 1. That's based on very few examples. But so it's, how do you know, what's the most obvious function you could think of that does that? This is the one I thought of, and this is my guess. Okay. For a field of dimension D, this is a bound on what I believe the splitting dimension should be. Here, dimension, I mean, you know, what's the dimension of a field? It's what you think the dimension of a field is. Which means I don't actually have a definite, well, I have like a kind of crappy definition, but I'm not going to put it up here. But okay. Yeah, number fields have dimension 2. Finite fields have dimension 1, for example. Okay. What do we know about H3, for example, as evidence of this? So for H3, you would expect from this that the third splitting dimension is 1. And it actually is. So now I'm going to give the fake proof, now that everybody is like totally lost or whatever. But okay, here's the fake proof of why it's 3. So this is a recent result with Arbeiter and Hartman. How does it go? Well, so somebody gives you a class in H3, and it has this stuff called ramification, which means the class kind of goes bad along some divisor. So here we're talking about a surface over a finite field. This is the particular case that our testing ground. So the ramification is a bunch of H2 classes over a bunch of curves in the surface. Now, these Brouwer classes themselves are themselves ramified, and there's this kind of Bloch-Ogus theory that tells you where they're ramified where they cross potentially. And the ramification of that ramification, these are ramifications of covers, so the ramification of a Brouwer class is a cover. So you have these little covers, the cyclic extensions at these intersection points. So what do? You carefully choose a cyclic branch covering that matches the cyclic extension at each of these like points. Careful, but you do it. And what you find is that if you do it right, when you lift it, you've killed the ramification of the ramification. These Brouwer classes are now unramified. But now an unramified Brouwer class, these are Brouwer classes over global fields that are unramified, they're trivial, which means the Brouwer classes are actually trivial, which means the original alpha is unramified. but now there's a result of Kato showing there's no unramified H3 on these things. And so this is an example of how one might prove this kind of result. So interestingly, you can bootstrap and get stuff about H3 in general. So I only have like 5 minutes left, so I'm gonna kind of like rush through this slide a little bit. But there's this, great idea by my former student Soren Gasabi. What he noticed is that a lot of the time when we were talking about splitting cohomology classes, the methods can often be used to not split a single class, but split any finite collection of classes just as easily. And when you do that, so he calls this the generalized splitting dimension. And if you're allowed to split a collection of classes, then it's an elementary consequence of Bloch-Kato that you can split arbitrarily higher cohomology just as easily. And so from this, you can actually get splitting dimensions for higher cohomology in a lot of circumstances. So this is really his observation. And combining this idea with that previous result, you can actually, and using this kind of field patching method that I'm not going to talk about, you can actually show for these families of fields and for H3, the conjecture holds. So this is the kind of expected number for these kinds of fields. Okay, so now in the last couple minutes, I want to mention that, if you already are inclined to enjoy the period index problem, which some of you are, I would like you to consider this other problem too. So there's this notion of behavior of a cohomology class that was introduced by Karpenko a while back in the context of the Brouwer group. What it is instead of just looking at the index of your class and the period of your class, you say, well, let's say my class has period p to the n. So then you look at its index, and then you multiply it by p and look at its index. Then you multiply it by p and look at its index, and you see how does the index shrink. And you call that list of shrinkage of index the behavior of the class. So it's, putting in these logs, it kind of is naturally a kind of like piecewise linear function. And you might ask, like, what natural behaviors show up for a given field? So I'm going to give you a conjecture just for you that I came up with last night. So, but I think I'm sure it's true. Okay. So my belief is that like the potential behaviors that you get are constrained by, by kind of like how close the cohomology class gets to like the maximal kind of period index bound. So in other words, if you have a kind of like, we can call this like a maximal criminal, it's not a criminal, it's like a maximal whatever thing. If alpha has like the biggest possible index, then my claim is that this B has to be strictly linear. So now, so you're basically, if what this looks like, if I was going to draw this, here I'll like draw this, right? You can see that kind of, right? Right. So it's like you have like this linear function, it's getting from here and it's like going down a fairly fast slope to there. That's like this kind of like what I'm calling aggressive behavior that I believe this thing must have. A priori though, there's no reason it might go like this and then go down or something, Like instead of going like this, it might go like this and like that or something, A priori that might happen. So what I'm saying is that I believe that it kind of goes down as quickly as possible, the soonest possible opportunity, the behavior for a kind of maximal kind of cohomology class. And why do I believe this? Because I have like one example. Okay. So it's really interesting. Like they weren't like studying behavior, but there was this really interesting paper of Eric Russell and Kelly McKinney and Eduardo Tingan, and they kind of looked at the behavior of Brouwer classes and kind of looked at kind of how hard they were to write as products of other Brouwer and stuff like that. And it comes out of what they did that exactly this holds, you know. So I'm sure it must always hold for all possible cohomology. All right, so that brings us to the end. I don't have a slide that says the end. That's the last slide. So thank you.
So we like to think of our classes in terms of geometric model. So you have an expectation for
Yeah, I mean, yeah, kind of. I mean, you know, so certainly there are some kind of higher categorical avatars for these, right? So like if you walk down the right hall in the right physics department and ask that question, they will say like, oh, you know, it's just this higher Ger, blah 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 blah. You know, they will have an answer for you. So you know, so there and I think, you know, it's even, you can even probably find it in the literature. I think, you know, kind of H3 classes being like corresponding to kind of two gerbs in the, you know, in the kind of classical more two categorical two stack framework. I guess I've been playing with this actually a lot. What I haven't been able to do is use it to do anything yet. So like, I mean, what we really would love, I mean, so actually, I mean, I bet that there is some kind of reasonably algebraic kind of like avatar, maybe in terms of like in terms of some appropriate finite-ish DG category kind of model that might, you know, but I guess the answer is I don't know. Sorry.
Yeah, so you know, previous slide, you showed that FT with two variables satisfies the set degree condition. What is the obstruction from getting like an algebraically close to three variables?
Oh, wait. So for wait, are you?
Oh, so this is three.
Oh, for this thing, I mean?
This.
Oh, okay. So you're saying what about like complex threefold, you mean, for example? I see. You know, I guess okay, so there is the big subtlety with looking at H3 for function fields is that, unlike with the Brouwer group and H2, there's a much wider gulf between geometric H3 and the field theoretic H3. Besides just the issue of ramification, it kind of like interacts with codimension 2 Chow group as part of the kind of like obstruction. And I guess I guess what I want to say is like there happens to be this result about triviality of unramified H3 on this, which really I don't think there's like, I don't know any analogous kind of statements in the kind of complex world. It's very difficult to kind of get a reasonable toehold on these things. But yeah, if there's something there, it's a different set of tools. You know.
Jeff Acker and I were wondering, does the postmodern period divide the postmodern index?
Yeah, I don't know what to say. I guess I brought that to myself. Yeah.
Right, so I think we could define the power of force to push the cut down.
Sure. I'm sorry, I couldn't hear that.
Maybe he's like. Index problem,
Oh, well, yeah, so this is an interesting, so I guess an interesting point is that, you know, there's like, kind of natural notions of what an index of an Asimai algebra might be. Well, so, and, or of a Brouwer class possibly represented by various Asimai algebras. And for schemes that are kind of like reasonably behaved, let's say quasi-projective regular or whatever, the nice fact is that the index of this kind of geometric Brouwer class is the index of the Brouwer class at the generic point over the function field. So, I mean, if you have a more exotic variety where you can't kind of like, then in that case, I'm not sure what to say, but it turns out, and this is like, in fact, a lot of the proofs of the index really construct geometric classes, and that's how they work. Yeah.
Similar with the last question, so a lot of the example fields were finite over something like the function field of affine space or the long
Yes.
series. Are there other geometric properties of other kinds of varieties that would give results on symbol length on unionship? Moduli stacks.
I see. So do you mean like, are there like kind of other kind of like classes of varieties where we might have like some extra information about kind of like,
Yeah, other than just being finite over affine space.
yeah, I mean, so I guess, yeah, I mean, I guess as we were kind of talking about in the postmodern period, you know, there's, or the contemporary period, excuse me, you know, we're starting to see kind of some results that are kind of leveraging some geometry of these varieties, and you know, for I guess there are kind of natural Brouwer classes that come up on a lot of interesting moduli spaces as abstractions. And there have been kind of nice, there have been some nice, you know, papers in the past, you know, by people like Biswas and Huggy, who have like, you know, kind of characterized what these classes are, took a look at their index and stuff like that. Yeah, I kind of more broadly, I mean, yeah, I'm not, I guess there's a, yeah, it is maybe it's kind of difficult, right? You're kind of looking for fields where we have a toehold on some extra stuff, right? And right now we have like a certain kind of list. There's a few more general things like Matsuri's result, where you just use like Diophantine dimension and get something, but those results, which are really the holy grail, seem very far off right now for the most part.
You were saying like that there's very little known about time, and there's like it's really like the numbers are really high for our results around line. Is there any, do you know any results in this kind of contemporary period using geometric facts, giving some bound on lines for more general L rather than just some power scheme?
Oh, well, so from a practical point of view, you can really always reduce it to prime powers. I should have mentioned that, but like, I mean, the point is like, you know, in these cohomology groups, you know, as just you have in any like torsion abelian group, you have like like kind of a primary decomposition. Any class is written as a sum of like p power classes for various p's. And you can really, because of the way index is defined as a GCD, you can kind of like specialize to each one and handle them separately. So I would say for like 90% of these questions, you can specialize to a given prime, and even where L is a prime and not even a prime power. Occasionally you have to consider prime powers too, but a lot of the times you can just reduce to a single prime.
Maybe we can leave, if there are more questions, we can leave for the break. Yeah, so thank you again.